Welcome back to DeepVisus, where vision meets depth. I'm your host, and in today's episode, we're diving deep into the fascinating question of how the continuous, dynamic activity of our brains might actually perform the discrete, logical computations we associate with modern computers. Our source for this intriguing exploration is Chapter 11, titled Universal Neural Field Computation, from the comprehensive book Neural Fields Theory and Applications, published in 2014 by Stephen Coombes, beim Graben, Roland Potthast, and James Wright. So, let's get right to our core question. Can the fluid, wave-like activity of neural populations truly execute the precise, step-by-step logic of a computer? To answer this, we'll unpack some fundamental concepts. First, let's understand what we mean by neural fields. Imagine not just individual neurons firing, but rather large, interconnected groups of neurons whose collective activity can be described as a continuous wave or pattern across a spatial area. These are mathematical models that capture the average activity of vast numbers of neurons over space and time. Think of it as a dynamic landscape of brain activity. Then we have the Turing machine. This is a theoretical model of computation, a foundational concept in computer science. It's a simple abstract machine that manipulates symbols on a strip of tape according to a set of rules. Essentially, if a problem can be solved by a Turing machine, it's considered computable. It's the ultimate benchmark for what a computer can do. Finally, Gödel numbers are a clever mathematical trick. They allow us to assign a unique numerical code to every symbol, every sequence of symbols, and even entire logical statements. This means we can represent complex information like the state of a Turing machine's tape as a single number. Now, how do these pieces connect? The authors of Chapter 11 propose a compelling bridge. They start by taking the abstract operations of a Turing machine and mapping them onto a continuous, two-dimensional space, often called a symbologram. Imagine this as a visual representation of the Turing machine's tape and internal state, where each point in this continuous space corresponds to a specific configuration of the machine. This continuous representation of a Turing machine is then described by what they call a nonlinear dynamical automaton, or NDA. This NDA is a mathematical function that, in a continuous way, mimics the discrete steps of the Turing machine. Instead of jumping from one discrete state to another, the NDA smoothly transforms points within this symbologram space, reflecting the computational process. But here's where it gets really interesting for neural fields. Instead of tracking individual points in this continuous space, which would be like tracking every single neuron, the authors shift their focus to tracking the evolution of probability distributions over this space. They consider how clouds of possible states evolve. This is governed by the Frobenius-Perron equation, a powerful tool from dynamical systems theory that describes how a probability density function changes over time under a given dynamic. Their key finding is quite elegant. If you start with a uniform probability distribution over a rectangular region in the symbologram space, representing a well-defined discrete state, the dynamics of the NDA will map it onto another uniform distribution over a new rectangular region. This means that even within a continuous, dynamic system like a neural field, the discrete, symbolic nature of computation can be preserved and propagated. They call this a dynamic field automaton, or DFA. Remarkably, they show that this Frobenius-Perron equation, which describes the evolution of these probability distributions, can be seen as a time-discretized version of the Amari neural field equation. The Amari equation is a fundamental model used to describe the activity of neural fields. This direct link means that the theoretical framework for universal computation can be directly implemented within the established dynamics of neural fields. So, to answer our initial question, yes, the chapter convincingly argues that the continuous, dynamic activity of our brains can indeed perform discrete, logical computations. By mapping the discrete states of a Turing machine onto continuous neural field dynamics and tracking the evolution of probability distributions within these fields, they provide a powerful theoretical framework for how the brain might achieve universal computation. This research opens up incredible avenues for understanding how our brains process information, from simple tasks to complex thought. It suggests that the very fabric of our neural activity could be a computational engine far more sophisticated than we often imagine. That's all for this episode of DeepVisus. Join us next time as we continue to explore the cutting edge of neuroscience and computation. where vision truly meets depth. Stay tuned.